Our next speaker is Dr. Thomas Loridan. Thomas is, he has a PhD from King's College. Which field actually? Wrote down weather research.
That's about right, yeah.
Okay. He is a catastrophe modeler specializing in tropical cyclone risk models. He has been lead data scientist or / catastrophe modeler in Europe and Australia over the last 6-ish something years. And now he is co-founder at RIASC. This is a brand new venture that applies state-of-the-art data science to natural risk hazard modeling. Please join me in welcoming Thomas to the stage. It's a pleasure to have you.
Right, good evening everyone, and thanks a lot Fabian for the introduction and for having me here tonight. What I'd like to do with the discussion tonight is introduce a model of tropical cyclone seasonal risk. So I'm well aware that most people won't be too familiar with tropical cyclones or with the type of modeling we use in this field, so I'll spend a bit of time doing a sort of tropical cyclone 101 introduction, and I'll discuss the sort of typical model we use in that field. The rest of the talk will be more about how we've brought some machine learning to the party and the sort of potential we see in there. But first, allow me just one slide on the company we started. So we started RIASC 4 months ago. It's 4 co-founders. 3 of us are very much from the catastrophe modeling background. So that means we've basically been building model of extreme event for the insurance industry. And the 4th person is Eugene Dubosarski, so most of you would have heard about. Eugene, the idea is to bring sort of Eugene's expertise and Eugene's wisdom to sort of modernize the way we do catastrophe modeling. So I'll talk a little bit more about that. I think if you asked Eugene what we're doing, he would say weather analytics. And that is a very good aim for us, but the truth is we are not quite there yet. We're not really looking yet at tomorrow's weather. We're still very focused on extreme events, natural catastrophes such as tropical cyclones. And we're trying slowly to branch out, and that's what I'll talk about tonight is our effort to do some seasonal risk forecasting. So can we quantify the risk for the upcoming season? So far we do that in terms of tropical cyclone, but we're quite interested to do that. For instance, what's the risk of having a particularly cold winter, a particularly hot summer, some droughts and things like this. So if anyone has interest for that sort of services, whether energy trading or agricultural sort of services, would be very keen to work in that space. And yes, finally I brought some stickers. We're very proud of our logo, so come and help yourself if you want one at the end. So let's start with a bit of an overview of tropical cyclones. What I'm showing here are all historical tracks, and the colors is showing the intensity of the cyclones in terms of the wind speed. But it's not really what I want to show for that. The really interesting, I think, is to show the sort of the geographical extent and the geographical distribution. So the first thing is that they're not necessarily completely global, but the tropical cyclones are a threat in very, very populated areas across the globe, whether it's the US, which usually makes the news, all of Southeast Asia, China and Japan, or outside of the world. A lot of threats from tropical cyclones. However, you can see that there are some geographical areas and some pockets where they're completely inexistent. That's the case around the equator, around South America, so everything in South Atlantic, and also at higher latitudes. To understand why, it's probably good to come back to what are the key ingredients that help or that allow tropical cyclone to form and develop. And there are really 3 really important ingredients. The first one, how warm is the water? You need very warm ocean. So the sort of idea is that anything below 26.5 degrees is too cold, and the warmer the better. Tropical cyclone needs a lot of heat, and the heat is derived from the ocean temperature. So that's the first thing. That's why they don't form at high latitude, so you don't get any too high. And that's why they sort of located close to the tropics. It's the name tropical cyclones. The second thing they need though is a fluid or atmospheric circulation that helps rotation. So they are spinning systems, like vortices, and this is really help with an environment that helps the rotation. So that's sort of the reason why they don't really happen straight at the equator. You sort of want the Coriolis force, or the rotation of the Earth, to help the system spin and get started. The third thing that really matters is to not have too much of what is called a vertical wind shear. So this idea that if you have very strong winds at two levels in the atmosphere, and they are pushing in sort of different direction, you will tear apart the cyclone before it really forms. So that's the third ingredient, and the one we're trying to avoid. And that's what is quite strong around the South Atlantic and so on. So that's why you don't have any over there. The reason I'm talking about those three is because I'll come back to those later on. But essentially, this explains why you get tropical cyclones in those regions in the world. The talk today is a little bit about how can we predict the risks that come with them. And I'll talk about that now. So how do we go about predicting the risk associated with cyclone? The answer really is it depends how far ahead you're looking. So the key thing is the lead in your forecast. So I've organized the slides in terms of how far ahead. And the first thing is the space between a few hours to several days. So that's the case where last year, for instance, you would have seen Tropical Cyclone Debbie form, and you sort of see that it will hit the Queensland coast in the next few days. So the question is, where will it hit? How intense will the cyclone be? And to sort of answer those things, we use a dynamical model, and these are deterministic forecasting tools. And this is very much the same models you would use to predict tomorrow's weather. So these are models that try to completely simulate everything that happens in the atmosphere, and we'll try to completely simulate the cyclone as it occurs. So it's not probabilistic at all. The idea to do that is you need to spend a lot of effort gathering the best picture of the atmosphere at the initial time you're looking at. So this is the input is very, very important. So you would take a lot of satellite data, a lot of observation from any type of ship and whatever you can find. And then your model, this type of deterministic model, will actually simulate every process in the atmosphere. So they will solve the equation of the flow, so Navier-Stokes equation for everyone interested in that space. But the key idea is that they will try and solve everything about the processes that leads to the output. And this type of model are very good. They've got better and better over the years, and especially with the increase in computer power. However, there is a very strong limitation here. Is the atmosphere is very famously a chaotic system, and we know that this type of approach cannot go beyond 10 days to 2 weeks. Even with perfect models, we know that's the famous butterfly effect, but any slight perturbation in your input will have completely contaminated your forecast after 2 weeks. That's the sort of theoretical limit. So you can't really use those beyond that. The way around is what is called dynamical ensemble modeling, and now you start to move into probabilistic forecasting. So you're not simulating one thing, but the idea is to get around this idea that the atmosphere being chaotic is you will use a range of models and a range of runs in which you slowly perturb the initial state. So we know that perturbation will completely contaminate your forecast, so we do on purpose contaminate and try simulating a whole range of different runs or sample numbers with just a little bit of different inputs. We also try different models, so most models are built in the same spirit, but they all have different approach to the way they do things. And the idea here is you're reconstructing a distribution of risk. So you're not looking just at one scenario anymore, you're looking at a whole bunch of them. That gives you an idea both of okay, the mean you can look at, but more importantly, you look at the spread of your risk distribution, and that's how you sort of move beyond the 2 weeks limit. So you can start to look at what's the probability of cyclone forming next month. This is the sort of tool you need to do that. And that works well as well because of the increase in computing power. It's always the story that this has made really big progress. However, to go beyond that sort of months forecasting, we sort of have to forget about the whole dynamical modeling aspect. And that's where I'll be talking about today, which is the idea of statistical modeling, which in many ways it's much less ambitious. So we're not trying anymore to simulate the processes. We don't try and simulate what the atmosphere is going to do. We're just saying we're interested in the link between the input and the output. And that is the sort of the main way to get beyond 1 month. So that's what we're trying to do today, is decide, is there a way to model the risk for the upcoming season? So say, I'll explain a little bit more here. I can summarize this whole attempt as saying, if I know the state of the climate at the end of spring, can I say something about the number of cyclones I should expect in summer, autumn, which is the peak of the activity? The sort of side problem with that is, how do you actually measure the state of the climate? What does that even mean? And that's how the talk will be focused on. So the approach we're using is sort of a two-step, and sort of illustrates a little bit how we've introduced machine learning to the process. The first step I'll be talking about is measuring the state of the climate. So this is very much using methods from the field of pattern recognition. We started with principal components, but I'll be talking about neural networks today. And that's the unsupervised learning bit. So we're just trying to extract pattern from the data we have. The second aspect will be the supervised learning aspect, is with these patterns extracted, how do we link that to the actual tropical cyclone activity? So these are the two main angles to the talk today. I'll start with this idea of measuring the state of the climate. So when you work in atmospheric science, this is the sort of data you have at hand. So very large gridded data sets. This is showing the sea level pressure. But you have that for a lot of fields. So you could have the temperature at different levels in the atmosphere, the wind speed, the relative humidity. So the list of variables is very long. And you quickly have a lot of data to play with. The sort of key aspect is what to do with it. How do you summarize this volume of data into something that atmospheric scientists can use? And really, that sort of has been the core attempt in climate science for a while, is how do we summarize that into some climate predictor, we call them. Researchers have done that by understanding the climate system, but also very much empirical analysis. One famous predictor that is being used is the so-called Southern Oscillation Index. And it's very simple. It's looking at the difference in the pressure anomaly between Darwin and Tahiti, just a straight difference. And it turns out that the value of that index is a good indicator of whether you are in El Nino or La Nina state. Now, for everyone here who's interested in data science, when you look at this, you probably think this is extremely simple. And that's what we've been thinking as well. It's surely neural networks might tell us a little bit of something else than just looking at Darwin and Tahiti. And that's sort of the approach we've taken. Can we improve on this? Can we find a bit more complex patterns that use a bit more of the data we have at hand? So how would we go about using neural networks? Well, this is a famous example of the MNIST data set, where you have gridded data. So instead of looking at a gridded data of handwritten digits, we can have our atmospheric grid of sea level pressure in there instead. And we could go about classifying, so using neural networks as a classifier to try to predict things like El Nino or La Nina, or patterns that we would have labeled before. The problem with that is we need to have a good idea of what the labels would be. So El Nino, La Nina, yes, this is something we know about, but there are a lot of things in the atmospheric system that we don't know, or at least we've not given label to. So the more interesting thing is to sort of use neural network in an unsupervised way. And one way to do that is what is called autoencoders. So instead of training a neural network to recognize a class, such as the digit number, you're actually going to train a neural network to reconstruct the same as the input. Sounds pretty useless at first, but it's actually quite smart. And the idea is input equals the output. You're trying to train the neural network to reconstruct the same, but you force the middle layer to be very narrow. So by doing this, you're essentially going through a process of dimension reduction. Because the hidden layer in the middle is extremely small, the algorithm will have to compress data into a higher level. Now, what's in those neurons in the middle layer is a really good way for us to have candidate predictors. Instead of the thing that used only Darwin and Tahiti, now we have a bunch of neurons that have used a lot more of the grids, and that have had to sort of reconstruct the input with this. So what we did next is to sort of look at what those neurons have done. So we picked one of them. So in the example I'm showing here, We've trained an autoencoder on the precipitation field. So it's precipitation anomaly, so it's been centered and scaled, but essentially just the amount of rain. We trained the autoencoder, and then we looked at the neurons in the hidden layer. So one of them is the one I've plotted here, where we've plotted only the strongest weights, so either very largely positive or very largely negative. These are the grid cells that really impact that neuron. Now, what's interesting is it's using a lot more than just the Darwin and Tahiti example. And it's also by just using the transformation that the hidden layer has used, or the neuron we're selecting has used, we can create a predictor from that. You can apply the same transformation, and given a certain precipitation anomaly and given those weights, you will come out with a single value which you can use as your predictor. So in this space, what you have as well is any area under the yellow colors. You know that a positive anomaly in the precipitation will tend to increase the value of your predictor. We'll call predictor A in the rest of the talk. And the positive anomaly of precipitation in the blue areas will decrease it. I won't go into the details of the physics in there, but what's quite interesting is actually this picks up on the El Niño La Niña patterns, for instance. You know that the way to really increase this predictor is to have a strong precipitation anomaly around Indonesia, combined with a strong negative anomaly in the east of the Pacific Ocean. Now, this is exactly what the La Niña phenomenon is. So, without telling the algorithm what to look for, it's sort of extracting things we know matter, which is great. The hope is that it's also extracting things we've never paid attention to, which maybe it does. So that's how we can just generate a lot of new predictors. The thing, though, is we quickly have a lot of predictors because you have a very large number of fields, as I was saying, but also for each of them you have a very large number of neurons. So the question is, how do we sort of filter the ones we want to use for the supervised learning to the ones we want to discard? And we've done a few processes to that. First, we've looked pretty stupidly as just what's the correlation with the target. So we take our weights, we look at the precipitation in March, April, May, for instance. We compute the predictor from this, and then we look at how, that's what's on the x-axis here, and we look at how it links to the number of hurricanes in the June to November that follows. So obviously we don't want to do only this, because we don't want to get into the overfitting of the predictor we select. But this is a good way to have a threshold and say anything that doesn't correlate to at least a certain level, we're not going to look at. The next thing to do, and that links to what I was saying in the introduction, is how well does the predictor link to the sort of key ingredients I mentioned. So we've looked at whether it correlates to the target, the number of cyclones, but we can look at whether it correlates to the sort of environmental favorable condition. So this is showing, for instance, that this predictor A, when it's positive in March, April, May, we will also likely have warmer ocean than usual in the North Atlantic, which is one of the ingredients I was mentioning. And we will have weaker wind shear, so this is these things that was sort of tearing apart cyclones, so this is a good thing. And it's also correlating to low pressure systems, also a nice breeding field for tropical cyclones. So another layer of tools to select which predictor which we would want to look at or not. Final thing is this sort of physical analysis I mentioned. So we sort of know enough about the physics that we can narrow down a few of them and say, okay, we'll go forward with those. Once we've identified some of them, we can move to the second step, which is supervised learning. And in everything we do in this sort of extreme events, natural catastrophe space, it's always very dangerous to rely too much on the data we have, because we have not much data at all. By definition, these are rare events. For tropical cyclones, the sort of rule is that we know well what happened after satellites came up, so after the 1970s. So that's sort of 50 data points we have. And so you can't get too caught into saying I'm going to have the classic kind of machine learning algorithm that will target these data built just in that space. We know that history is also just part of the story. We know that what happened is just one thing that could have been very different. I know that the extreme value are not being caught in the last 50 years. So all of this is just saying we have to be careful with the type of algorithm we use. And what we've done is to go down the way of Bayesian modeling. General concept would be that past records, all these historical 50 points we have, there's just sample from a distribution. There's nothing special about them. What we're really trying is to reconstruct the distribution behind those points. I'll give you one slide about my understanding of the mechanics of Bayesian modeling, and then we can talk more after on the question if anyone's interested. But the general idea is you start with a prior belief, you start with a distribution of the risk, and in our case it's very important. You don't just rely on the data points. You have something, and in that case it would be, for instance, if we look about hurricanes, we'll have a distribution that says we'll expect around 11, 12 hurricanes a year, and that's the sort of probability. There's no reason why they wouldn't be over 30, even though that's never happened in history. And there's no reason why you wouldn't have just 0 one year. So we just start with something like this.
Singularity.
Then you start to add the data. So just showing since the 70s where we know pretty well what happened. And the data will help you, well, first it will help you refine your prior. So your distribution will be more consistent with the data you're showing it. But more interestingly, it will also help you make the distribution conditional on the state of your climate. So in this case, let's talk, the state of the climate is just this predictor A I've described, but you can have a lot more of them. And once you've added data, you've updated your prior, and you have a conditional risk distribution, which means that for years where the predictor is pretty strong, you end up with a distribution that is more to the right. You have more risk. You can still have 0 hurricane that year, but the distribution is now conditional on what you know from the climate. For years where the predictor is low, it's the opposite, and the distribution is more to the left. So that's how we build the model. We've made it a global model, so it has 6 basins, as I was showing in the introduction, and as well as 3 different levels of intensity. I'll be showing a little bit of sort of backtesting here. And the first thing is to show risk when we don't do any conditioning on the climate. So just every year is the same. On the x-axis you have the number of hurricanes, and you would model that as a Poisson distribution with a mean around 11, 12, as I was saying. No knowledge of the climate. And on the y-axis you have the same for the typhoons, so tropical cyclone around Asia. Bit more activity there. I will leave the white circle on the plot so that we get a sort of reference to this case with no predictors at all. And then I'll show what happens when you take into account the climate. So that's for 2017, last year. If we had made a prediction last year before the season started from knowledge of the climate, we would have had our model predicting a lot more weight in that space. So more activity in the Atlantic and less in the Pacific than the no predictor case. And as it turns out, last year that would have been pretty good because it was a very, very active season in terms of Atlantic hurricane and a pretty average one for the typhoons. Now you can repeat that. We've done this as a leave one out evaluation, and what you're saying is everything in the last 40 years. Now it's not always perfect prediction, but the really important thing for us is that it does better than the white circles. More often than not, the yellow area is on the same side of the white circle as the dot. Good, 2 minutes? Yeah. Right, so that's sort of backtesting, and it's in a way not the most honest way to do the backtesting because we're doing a leave one out evaluation, but we're still having data about things that happen after that. So I think the real test is what we did this year, which is to make a forecast. So just before the season started this year in the Northern Hemisphere, so at the end of May, we made a forecast for all the different basins. And to date, well, I'll focus on the North Atlantic actually, because that's the one basin where most people collect forecasts and have a lot of interest. We had a pretty big window, so those windows of numbers we quoted are supposed to be around 65% probability. And that's because our model has not been very confident in the North Atlantic. This is the distribution we had as a forecast. So named storm, category 0 storm, the weak ones. And the line you have here is the long-term average. So what we forecasted for this year is that we would have more activity than the average in terms of weak storms. For the category 1 and category 3 ones, would fall back into the long-term average. So we're thinking this year would be pretty average in terms of the strong storm, but quite active in terms of the weak storms. That is sort of the same message differently. Now, as I was saying, the North Atlantic is the place where a lot of people do this type of modeling, so we can compare to our peers, and that was before the season started, how the model stacked up. Ours is here, and we are a little bit higher than others, especially a little bit higher than the US agencies or the UK Met Office for this case of the weak storms. Now, to date, the jury is still out. So this is sort of a website from Colorado State University that tracks the activity to date. So to date, we've had 5 of those Cat 0 storms. And on average, you would expect 4.5, so pretty much on the average. Same for the number of hurricanes, and pretty much for the major hurricanes. So to date, everything is sort of following climatology. But we're just about to enter the month of September, which is the biggest month for hurricane. And this is one of those web pages, weathermodel.com, which has this sort of dynamical modeling approach I was talking about at the beginning. And this is where they look at for Tuesday next week. So they think there should be a bit of activity starting maybe 1, 2, or even 3. Low chance of tropical cyclone starting close to Florida. So that's, the next month will really tell how our forecast does this year. That's it. Thank you very much.
Thank you so much. It was great. Quick question?
It's not a quick question, but I think it's an important question that has to be asked.
Is it a small presentation thinly veiled as a quick question?
Okay, hashtag singularity.
That starts well.
Frame of reference could shift for your models. You may not have a black swan, you could have a unicorn situation here. Your models may no longer apply once you go past a point of no return. Is this in play, this concept?
Yeah, I mean,
do you understand what I mean?
Yeah, no, absolutely. And I think that's a big problem with that field. This is not stationary. Climate has changed. Climate is famously changing.
State change.
But the thing is, it's better than
nothing,
right? What we're showing is.
But what are we doing about it, mate? What are we doing?
I think the question.
It's time for thinking. We've got to do something.
I agree.
Sorry.
And I think without going to the
beyond semantics, this is pragma.
No, and without going too far into complete unicorn, as you said, just accounting for climate change is hard enough because we don't really know exactly how it will impact the location of the risk for tropical cyclones. So building models like we're doing, but accounting for climate change is already a good challenge. Then
You're
we can
on a
talk
good
about.
track, but we should talk more. Yep.
Arnie, please.
Hi.
Yes.
Quick question. Actual quick question. Did you look at sequences of changes? So, for example, a convolution layer or an LSTM. Does that sort of make sense for what you're looking at?
Yeah. So I should have mentioned that out of the 2 parts, I've done the second one. So the part about the neural networks is my colleague who's done that. But yeah, he's looked into convolutional neural nets. But I think every time he came back to the more simple option that we could track. And yeah, I think the answer is yes, he's tried, but we've not selected those things at the end.
Yep.
Yeah.
Thanks, Thomas. As far as I understand, all neural networks are fundamentally idiots, even the ones that are fed with a pre-trained model, because they don't have any sense of rules. They learn entirely by assigning weights to nodes and just following the patterns in the data that lead them to the least error. Is there any way to incorporate a knowledge of the laws of physics? Can you drive the the weights using the Navier-Stokes equations and thermodynamics, for example?
Entropy.
Yeah, I don't know. I think in that case, the way we're using through the autoencoders is really just reconstructing the input. Could you use, I don't know how you would use Navier-Stokes to help the weights. I mean, if you have an idea, I'm really curious. I've no idea.
Any other questions? Or?
Yeah, back.
Yeah.
That's a quick one. What's the difference between a hurricane and a typhoon?
I wanted to say it, but I forgot completely at the beginning. No, they're all tropical cyclones, and then depending on where you're in the world, they have different names. So if you're close to the US, they call them hurricanes, and Southeast Asia and Japan, they call them typhoons, but they're exactly the same thing. Oh, sorry, I didn't mention that was part of the plan.
Hi. How did you predict the multiple times ahead? Did you use like input for the next month for the sequence one, or multiple models for each month that you're trying to predict?
So we've done it in this case I presented. What we've done is to stop 1st of June. That's the official start of hurricane season in the US and different places. And we've used March, April, May as the key period for the predictors. Some are just the months of May, some are just averages over the three months period. So that's, using March, April, May as a predictor of June to November activity. That's the sort of window we're looking at, yeah.
Did you predict like more? Did you use that as input for the next, or only 3 months?
No, we've only done that window of June to November. Yeah.
Regarding the Bayesian hierarchical modeling, could you go into more detail? Like, did you use MCMCs, or how did you? I mean, you said prior, and then all of a sudden,
Yeah.
And I was like, wow, you talked about the neural net.
No. I've used MCMC. Well, what I've followed initially on Eugene's advice is Richard McElrath's course. I don't know if it's called the Rethinking package and Rethinking. I really recommend it. It's like a bunch of lectures online that I've really, really enjoyed, and I've pretty much followed his whole procedure. So yes, this has been done with the MCMC sampling.
Okay, let's conclude here. Thomas, thank you so much. And now I think it's time for announcements. Perry, do you want to go first?
Sure. Hi, I'm Perry. I'm from the Commonwealth Bank of Australia, which you may recognise from the sign out the front. We're probably one of the biggest data science teams in the country, and we're always hiring, and we do interesting, exciting work, as you'd expect of any company that has as many customers as we do. So if you're interested in a career in data science, potentially here, come have a chat. If you're interested in data analytics, data engineering, all of the things that we hire for, we're constantly hiring. Do come have a chat if you want to know about the sort of work that we do. We also have Ravi over here on the end of the room, who's from talent acquisition. So if you want to know technical details of how you get hired in real life, he knows more of those than I do.
IRL.
Yeah, just come have a chat. Thanks for coming. Please don't forget to hand in your passes on the way out, otherwise we'll chase you down and make you come back to this building and hand them in to us. Thank you.
Thank you. Any other announcements? Yes.
Hi, I'm Andrew from the Digital Transformation Agency. I'd just like to promote GovHack, which is happening the weekend after next. So the 7th and 9th, there are various venues. I think we've got one somewhere in Sydney. I couldn't see it on the website, but definitely somewhere in Parramatta. It was on the website. There is fame and not a whole lot of fortune to be won. But you get to play with lots of open data. Kudos and do amazing things and have a great time. If you are interested, maybe you don't have a team yet, maybe you have a team but you are looking for some more skills, or maybe you just like socialisation. There's a connections event that's happening on Friday. I believe that's down at UTS in that direction, but not very far away. That's 6:30 on Friday. Otherwise, I would just simply draw your attention to govhack.org. All of the information, apart from the location of Sydney venue, is up on that website. I'm sure in the next week they will pinpoint exactly where you'll be going for the Friday for the Sydney event. Or if you're interstate, there are venues all over the country. So if you have any sort of vague interest in public data, data provided by government agencies, that's even vaguely interesting, have a look at the website.
Just do it.
govhack.org.
Just do it.
Do it.
Do it.
Thank you so much.
Woo!
Anyone else?
Thank you.
Greg Pearl had to leave earlier. He sends his regards as well. If you're interested in being recruited in the data science space, he is one of the key people to talk to. He works for Endworld, specifically focusing on the startup space, but he has worked in the space for so long. He knows what's being sought after at the moment, how to get into the field, or how to make your next career step. His details are on the Vita website as well. Anyone else? Announcements? Cool. New job offerings?
No
opportunities? Go for it, whatever it is.
Hi, I'm from Microsoft. We're running a open hack machine learning. I think it's like a 3 to 4 day event next week. Open to anyone. If you just go hunting around for open hack machine learning Sydney, this kicks off on September the 4th, and it's done at Clifton's. So it just sounds pretty smooth.
Okay. Well, thank you.
Thanks.